Welcome you all to a new session. In this session, we are going to see synchronous sequential circuits. In the previous units, we have seen the circuits based upon memory storage elements like flip-flops and latches, and then we have seen registers and counters. In this new session, we are looking after the synchronous sequential circuits, which are also sequential circuits part 2. Now, what exactly mean by synchronous sequential circuits means the circuits which are in synchronous with the clock. Such kind of circuits we call it as synchronous sequential circuits. Now, you can see the basic definition. A synchronous circuit is a digital circuit that uses clock signal to synchronize the changes in the state of a memory element. The data is stored in the memory devices called as flip-flops or latches in sequential digital circuit. Now, what exactly the synchronous sequential circuits are to be designed in this part means we are going to design the circuits which are in sync with the clock. And what kind of devices those are, like we are going to see serial binary generator, serial bit adder, or sequence generator, sequence detector. So those kind of circuits we are going to look after in this particular chapter now. Now, what are the steps involved? What is the basic steps which are involved in designing these sequential circuits? The basic steps are getting the circuit specifications. I need to know what are the specifications of that particular circuit. First one. Next I am going to create a state diagram. State diagram means the diagram which is going to tell when a state should get transited from one position to the other position. For example, if a variable is at a is equal to 0, so that a is equal to 0 is represented as a state. Now, if a variable is at a is equal to 1, so that particular thing we are going to call it as a state 1. So those things are called as creating a state diagram. Next, with the help of state diagram, we are going to create a state table. State table, after that we are going to reduce the number of states in our particular design. After that, we are going to choose the number of state variables, means number of variables which are required to represent those states. And selecting the type of flip-flop, means whether I am going to use SR flip-flop or D flip-flop or JK flip-flop or T flip-flop. So what type of flip-flop we are going to use. So that kind of selection will be done in this particular line of steps. The last one, deriving the logic expression, means I need to derive the required logic expression to serve the outside world. So that logical expression should be derived here. The last one is constructing the logic diagram. Once BE like Boolean expression is derived, with the help of Boolean expression we can draw the diagram using logical gates. Okay, let's begin with our sequential circuits. Now, synchronous sequential circuits, here we are going to have finite state machines, that is stands for FSM. Now, these finite state machines are of two types. They are Mealy machine and Moore machine. These are the scientist names, that is Mealy and Moore. Now, this Mealy machine and Moore machine, how they are going to define for this finite state machine, means they are going to have finite number of states in that particular machine. You will be also having machines with infinite number of states also. But here in this particular chapter, we are going to talk about only the finite number of states. So that is the reason finite state machines are of two types. One is Mealy machine and the other one is Moore machine. Now, how does this two machines are visible in a block diagram and what it is going to define, we will see here. Now, see here. This is Moore machine. Moore machine is the output is the function of only present state, means output is going to depend upon only the present state. And what does actually Moore machine contains? It contains a transition logic, a state memory and a output logic. Now, for this one, this transition logic I am going to apply a input value here. When an input value is applied, that input value will go through transition logic and it gets stored onto a memory. And that memory is going to provide a current state through the output logic, and that output logic is going to provide an output value. Now, this particular value, the current state, is always fed along with my input again. So that input along with my current state, again it is going to produce a transition logic here. So this is how a sequential synchronously in respective with the clock, it is moving the content, and this is always depend upon only present state. So that is what you need to remember for Moore machine. Coming for Mealy machine, the output is function of both present state as well as input. Means it is not depending upon only the present state, it is also depending upon my input value also. Now see here I am providing my input here to the transition logic, along with the transition logic that is connected to the state memory again connected to the logic gate with the current state. I am feeding my current state along with my input, as well as the output logic is connected with my input value also. So that's the reason it is telling that output is a function of both present state as well as input. So you can observe clearly this input is connected at output logic, current state is also connected to the transition logic along with my input. So my output is always function of present state and input here for Mealy type of machines, whereas Moore type of machines the output is function of only present state. Kindly remember these two statements which are very very important to differentiate Mealy machine along with the Moore machine. So this is what related to finite state machine. We'll see with an example so that you will understand how these machines are represented in a real time. Now, state diagram. As I told you, as a process of basic steps which we require in designing these synchronous sequential circuits, as a part of our circuit designing, we require state diagrams and state tables. Now, these are some of the state diagrams of our flip-flops. As you know that we already have flip-flops. That flip-flops, those are SR flip-flop, D flip-flop, JK flip-flop and T flip-flop. Now you know SR values directly, you know SR values as S and R, and output you know as S00, 01, 10, 11. So for 00 it is no change, for 01 it is reset, for 10 it is set, and for 11 it is undetermined. This is the functionality table of my SR flip-flop. Now how this particular functionality table can be represented using a state diagram now. Either you got 0 or 1 value. With the help of this particular table, I can tell that it contains only either 0 value or 1 value. So I am taking a 0 as one state, 1 as the other state. So I am considering 0 as one state, 1 as the other state. Now when this transition occurs between 0 and 1, we will see now. Now see here, when this is a 0th state, 0 state means it is not going to, it is going to be here only for 0, 0 value and 0, 1 value. Now see here, for 0, 0, no change, means whatever the state it is going to be there, it will remain in that particular state only, that is no change. For 0, 1 it is reset, reset means the value is 0, right? So that is the reason it is going to remain in the 0 state for these two values. Next, when the transition is going to occur from 0 to 1, 0 to 1, when the input value of 1, 0 is occurred, the set value is going to appear, that is 1. So for 1, 0, the transition is taking place from 0 to 1. Now state, it is remained under one state now. That one state will be there till for what input values, that is 0, 0 state again, and for 1, 0 state. So it is going to remain in that particular state for 0, 0 and 1, 0. Now again it should come back for initial state. Now when it is going to come back? It is going to come back for 0, 1 state. Whenever there is an input value which is occurring as 0, 1, then again it will move back to its 0th state. So this is the diagram that we are going to call it as a state diagram. State diagram is purely drawn based upon our functionality table only, right? Let's see with the D also, D flip-flop. You know D flip-flop, D and output. For 0 it is 0, for 1 it is 1, right? Now 0 and 1. Now for 0, D value is 0. It will remain in the D state only, that is 0 state only. When D is equal to 1, it will remain in this particular 1 state only. But when the transition occurs between 0 and 1, when D is equal to 1 occurs at S0, 0th state, then the transition will occur from 0 to 1. When D value is produced as 0, then transition occurs from 1 to 0. So this is the transition between 0 state and 1 state under D flip-flop. Coming to JK flip-flop. Now under JK flip-flop, you observe clear. Now you know the J and K functionality table also, output. 0, 0, 0, 1, 1, 0, 1, 1, right? Now for 0, 0, you know it as no change state. For 0, 1 it is 0, for 1, 0 it is 1, for 1, 1 it is toggle. Means it is moving in between 0 and 1, 0 and 1, 0 and 1. So that particular state we call it as toggle state. Now see here, 0 state and 1 state. It will remain in 0 state for 0, 0 condition and for 0, 1 condition. Right? That is what the functionality table is also representing. Now when it is going to go back to for 1 state, whenever j and k value is 1, 0 or 1, 1. Now whenever the inputs occurring as 1, 0 or 1, 1, it will travel from 0 to 1. Now it will remain in 1 for what are the cases? For 0, 0 and for 1, 0 state, it is going to remain under 1 state. Again from 1 to 0, when it is going to come back, when 0, 1 is occurring, means for this particular state, or when 1, 1 is occurring, means it should travel to 0 state from 1 state. So this is what the transition takes place between 0 and 1. Now basically this functionality table we can also call it as a transition table also. You know, state transition or state table we call. These things are called as state diagrams. Now based upon state transition tables, we are going to represent the present state and next state also. Why? Because for 0, next state is 1, for 1, next state is 0 here, right? Similarly for T flip-flop. Now T flip-flop, it will remain in 0 state for T is equal to 0 and it will travel to 1 state when T value is 1 here. Now when it is traveling to next state from 0 to 1, what happens? It will remain in that particular state till T is equal to 0. This is T is equal to 1 beta. This is T is 1. It will remain in T is equal to 1 state. No, T is equal to 0 only, T is equal to 0 only, it will remain in the same state. Why? Because for T is equal to 0, 0 is 0 the same. If T is equal to 1, then only the 1 transition again takes place from 1 to 0h state. So this is how we represent the functionality tables for state diagrams. And this using state diagrams, we are going to tell the state tables also. These are state diagrams. Now coming for state table also, I will represent that also for you. For a D flip-flop I will tell. So D is the input, present state and next state. Now present state is 0 if D is equal to 0. So it is going to remain in 0 only. 0 next state, what is the next state? It is 1. Right? Now if D is equal to 1, then D is going to remain in 1 state only, that is present state. What is the next state for 1? It is 0. So this particular table I am going to call it as state table. This is called as state diagram. So with this introduction, with the help of flip-flops, you might understood for a finite state machine, you are going to have a state diagram, state table and a functionality table. Now for all finite state machines, we are going to represent this way only. Right? So these are the output values. These are output values. Now the same machines can also be drawn for the representation for Mealy as well as Moore type. These are state diagrams basically. Now how we differentiate the Mealy machine and Moore machine, we'll see in the next session. Okay, thank you all.